Hello students, a warm welcome to the session. The session is about mathematics of cryptography. See, the cryptography is very simple when we are discussing about the basic operations. Now, this session is specifically on the symmetric cryptography. Symmetric is itself saying that same. So, same indicates when we are going to utilize the same key, then in the encryption and decryption process, then we say symmetric cryptography. In the symmetric cryptography, what may be the mathematics we are going to include in our session today? Let's have an outlook first, then we'll be having each and every session in detail. See, in the symmetric cryptographic mathematics, we are going to discuss first algebraic structures. So in the algebraic structure, this will be totally dependent on the sets of the values, right? You'll be having group, fields, and rings, right? Lagrange's theorem and Galois field will be new things to you. So let us discuss this. And polynomials is very familiar to you. Let's enter into the session now. Coming to the algebraic structures. See, when we say what is algebraic structures, the term itself saying that a set of elements when we are grouping together. A set of elements when we are grouping together and performing some operations on it, then we say algebraic structures, right? A set of elements which are grouping together and performing some operations on that, then that set of elements will be called as algebraic structures. These structures are hierarchically divided into three types: groups, rings, and fields. Groups, rings, and fields. Let us have a small differences between these. See, groups is a set of elements where it is going to perform with one binary operation. Okay, groups will be with two or more operations, maximum two operations. Okay, fields also will be with two operations. Clear? Now, groups. So coming to groups, we say a group is a set of elements which are going to perform with one binary operation. Okay, one binary operation. And these operations will be valid when a set of elements are finite set of elements. If the elements are finite set of elements, then we say that group as finite group. Okay, we say that group as finite group. Otherwise, that is obviously the vice versa as infinite group, right? And we say a group as cyclic when repeated elements are keep on applying with the same binary operations, that is a into a into a into a into. So this will be leading to an operation a to the power of n. Okay, so this is a combination where we are going to discuss about the groups. See, all the groups are combinedly together with one binary operations. So when the operations are repeatedly happening to the same set of elements, then we say a to the power of n, and we say that as cyclic group. Don't forget this term, cyclic group. See, there are four terms we have included, that is one binary operation, finite elements, finite group, and cyclic group. So these are the things which you have to remember for your exam point of views. Coming to the ring, so rings are performed on two operations. Okay, that may be plus operation, addition, or multiplication, or whatever it is. So rings will be concentrating on the two binary operations. Fields also similar kind, two or more binary operations. Okay, so first of all, let us know the basic differences like this. Even rings and fields both are also set of elements itself, but the main difference is two binary operations is the main difference things. Okay, so as you can see in the table below, this table is giving you one structure, the typical operations which we are going to perform, either this or that in the group. See, one operation we said, right? In the ring, we can perform two or more operations at the same time. Right. So let us move with the next slide where we are going to have It's all properties when we are discussing about the set of elements. See, closure properties are nothing but, see, I am confident that all the students by this time you will be understanding all these properties. See, closure properties are nothing but if there is an element A and B in G, which belongs to G, its operation, whatever the operation output also must be belongs to G. That is a closure property. Very simple. There are a number of elements we have in G group. Okay. We say ring and field also sometimes group, because when we are going to operate multiple operations, we are going to include that as a set of elements. Now, A comma B belongs to G means its operation output also A into B, this also should be belongs to G. Associativity is the thing where we have two or more operations. See, A into B plus C. So if I have elements like this, its expression evaluation must be also includes in G. It's very simple, right? No, next one is commutativity. See, a group is called commutativity when A plus B is equal to B plus A, right? Identity. See, identity is very simple when A into some identity property equal to E into some identity property will be our element itself, right? Inverse. So when we have A into A dash equal to A dash into A will be equal to some value that is either 0 or 1. Okay, if it is plus operation, A plus minus A equal to, obviously it's a 0. Similarly, minus A plus A, that is equal to 0. So this may be, see, if it is A into 1 by A, so that is 1. So here the output is 1, here the output is 0. See, these are the some of the properties which we should know before knowing this, all the algebraic structures, right? So if we apply all these properties on the algebraic structures, then one after the other you will be understanding the set outputs. So this is about algebraic structures. Now let us move with the next concept, that is Lagrange's theorem. See, Lagrange's theorem is a theorem where we have a G as a group. See, we have a G as a group and H as its subgroup. So subgroup may be any part of the original group G. See, any part of the group if we say, then H must divide G for sure. Okay, that indicates that G will be the larger and H is a subgroup. So where H must be dividing G for sure. Okay, so this will be very clear. Next, Galois field. See, Galois field GF will be giving one statement that I am the prime number. I am the prime number with some power value. See, prime will be the base value and exponent will be some any integer, any integer. So let us see, let us write 8. So my prime number, basic prime number is 2. So if I give 2 power 8, my Galois field is 2 power 8 means, see, this is plus 8, don't take it as minus. If my value is 2 to the power of plus 8, then I can have maximum 8 elements in my expression. See, that expression may be anything, polynomial or whatever may be. So the 2 power 0, 2 power 1, 2 power, so like this, I can have 2 power 8 maximum. See, if I take in place of 2, if I take some x, so maximum x to the power of 8 can be accessible. That's it. Okay. So, but P must be a prime number and N must be N may be any prime, any integer, right? So this is about Galois field. Now, next one is the polynomials. See, polynomials are some expressions with some coefficients and the exponent to the power of, say, base to the power of exponents. Now, why this is important in cryptography? See, when we have a polynomial like this, its bit word can be written as its bit word can be written as, see, x to the power of 0, as we are having x to the power of 0, I am taking as 1. X to the power of 1, see 0. X to the power, see, as we are given the polynomial properly with the coefficient values, I am taking this as like this, right? Now, after evaluation, x to the power of 7, as it is 1, so I am taking it. Zeros part I am excluding. Obviously, right? We do that. We do this, the polynomial additions, multiplications kind of thing. So my value is x to the power of 7, x to the power of 4, x to the power of 3, and x to the power of 0. This. So my final value is this one. Now, if any normal polynomial is given like this, next in reverse order, see x to the power of 0 is there, right? So I should place 1. X to the power of 1 is not there, 0. X to the power of 2 is not there, 0. X to the power of 3 is there, we take 1. X to the power of 4 is there, we take 1. X to the power of 5 and 6 are not there, we take zeros and zeros. X to the power of 7 is there, 1. So this is the 8-bit value I can have in my encoding or decoding process. So in a reverse order or else in the forward process. So the same thing we have done to this example also. See, I have these values as a basic thing. See, x to the power of 5, x to the cube plus. So only these terms I should have as ones, remaining 8-bit should be 0. Okay. So in this way, we are going to identify the polynomial into binary formats. Clear? Now, see, prime polynomial is a polynomial which is given as a input. Now, irreducible polynomial is a polynomial where the value which exceeds the Galois field. See, Galois field I have given as only 2 to the power of 8. See, let me write x to the power of 8. But it is exceeding x to the power of 12. So I should not have this in my terms, right? So for this, I should go with modulus operator. Okay, with respect to the irreducible polynomials. See, where we have the degree which is less than n, then we say irreducible polynomials. If you are going to exceed, then immediately we are going to apply mod operation. Clear? See here, x to the power of 8, x to the power of 12. So mod operation, whatever the remainder we get, so remainder will be my output. Very simpler thing. X to the power of 8, we perform with, see, as it is 12, I should go with, see, here it is 8, so into 4, I should go with into 4. So 4 is nothing but 12. Next 4 plus 4 is 8. 3 plus 4 is 7. X 1 plus 4 is 5. See, here we don't have anything, x to the power of 4 directly. So we are going to cut off everything, and whatever the remaining x to the power of 8 plus x to the power of 7, x to the power of 8 plus x to the power of 7 is also gone, right? X to the power of 7 is also gone. See, we have two terms here. Next, x to the power of 5 is remaining, x to the power of 5, x to the power of 4, x to x square. So whatever is remaining, I have written, right? And again, I'm multiplying with 1, and whatever the value I get, see, 2 power 8 is my, means 8 bits I can have. Galois field I can have, 2 to the power of 8 means 8 bits I should have. So until I get 8 bits formats, I should go with the remainder format. So once I get the remainder format, then I should stop that. Clear with this? So these are few examples, same type of examples which we took to perform this. So if you have any queries, just place in the comment section, or else you can make me directly to clarify your doubts. I am always ready. Thank you.